I emailed the moderator. Did you get that? Sure.
You can actually sit down.
We're meeting with Regina and Pam and Emily, and I are meeting next week to talk about the hybrid format. It actually went pretty well last time, thanks to you pulling Ann in. That was that was.
Already doing great.
Just break. Yeah. Start losing our audience members.
864. Well, I was gonna have you pick up any, like I was gonna have.
We're actually going to have online. This is how.
If folks online have questions, there will be like a red bubble that comes up in your chat or your Q&A. And if you just click that, you'll see. Yeah, and then I'll leave it out.
And then
Okay. If you will need an extra minute or two at the end, that's fine.
And are they in as moderators? No. All right, hold on one second.
If you want to take this up. Set that up there. You want to snack watch? You want to know when it's 10 minutes or just 3?
3 will be fine. Good afternoon. We've got some technical difficulties up here. We're going to get those straightened out, but welcome to the section on Falls Lake nutrient management, and glad that you're here today. I'm going to do the first presentation. I'm Forrest Westall with the Upper Neuse River Basin Association, and I'm going to give a little background on the program and how we are doing where we are now. So the UNRBA is an organization that was created back in 1995. It is all aimed around the Falls Reservoir. Falls Reservoir is a Corps of Engineers project that was controversial from the start. Probably started planning in the 1950s. It went through the process of approval. And in the 1970s, the state of North Carolina, which I was actually working with then, they recommended in the Department of Natural Resources and Community Development, recommended not to build the reservoir, but the state, the governor overruled that, and so it was constructed. It is a multi-purpose reservoir. It was originally created for the purpose of flood control in the lower part of the Neuse, but in reality, one of the highest and best use that has come out of this reservoir is the city of Raleigh has it for water supply. It serves about 550,000 customers. It also provides aquatic habitat. There's several fishing tournaments and recreation that goes on in the lake. The estimates that we had of the lake being unusable from a trophic standpoint did not come true, thankfully, and the lake has been generally in pretty good condition. Again, it was constructed in 1978. They started to fill it in 1982, and I was there for the filling of the lake. They closed the dam and we were there, it's only 40 years old. So this is the 40th year of that lake. It is a drowned river, as everyone knows. It was a river, a stream that was in existence before the dam was closed, and it became a reservoir. And as a result, there was no evolution of this lake into a real lake. And so it has been in the process of stabilizing since that time. Obviously, if you can see the graphs there, you can look at the levels of chlorophyll A, of total phosphorus and total nitrogen after the lake was filled. There was a lot of debris and leftover material left in the lake. And so when the lake filled up, there were issues there. Since that time, our study began in 2014 and we studied through 2018. You can see the relative reductions in these water quality measurements during that period of time. As I said, the UNRBA was created in 1995 as a forum for discussing Falls Lake, what was going to happen with Falls Lake, what kind of management would need to be done on Falls Lake. And obviously the city of Raleigh has been very interested in making sure that Falls Lake gets protected. This watershed also contains water supplies for the South Granville Water and Sewer Authority, for the town of Hillsborough, and for the city of Durham. So it is a water supply in a water supply, and there's lakes and ponds in those areas that are used for water supply. And just to give a perspective of this, if you assume this reservoir, the drainage area for this reservoir is developed, it's not. It is mostly wooded. And it is, that's one of the factors I'll show in just a moment. The goals of the UNRBA: in 2012, I became the executive director of the UNRBA, and we focused on the study of the lake, evaluation of the lake. We went through a process to define what we were going to do, how we were going to do that. We sent those documents to the state of North Carolina. They approved it. The rules included a provision that would allow for an assessment of stage 2. It's broken into 2 stages. And so our goal was to use a science-based approach to develop information that would clarify and give us a better idea of how this reservoir was functioning, how the watershed was interacting, what things could be done to manage it more effectively. We believe that science is a good lead-in to management decisions. It is something that you want to have as a basis for making management decisions. Sometimes science doesn't give you the answer, but it gives you the information you need in order to make a good judgment on it. And we're trying to balance policy, science, water quality goals. And as you can see in terms of the challenges for the lake, it has exceeded the 40 microgram per liter chlorophyll A standard essentially since it was constructed. It had values in certain areas, particularly the upper parts of the lake and the arms of the lake. It exceeded 40 micrograms per liter of chlorophyll A, not unexpectedly. And that second bullet there indicates kind of the challenge that we're looking at. Our modeling on the watershed, which Alix will do later on and talk about that, 74% of the watershed is unmanaged land. It's either forest land or what I would call vacant land, grassland and shrubland. This is areas that were probably in agricultural production or pasture before, and it's just been left to grow up. And also wetlands and water surface itself. The watershed and produces the sediment that comes in, the organic carbon, and that settles out in the lake, and the lake ends up cycling nutrients. So the lake is a nutrient cycler. The management strategy for the lake, it was broken into 2 stages. The first stage was aimed at meeting the water quality standard in the lower portion of the lake, where Raleigh takes its water supply near the dam. That was to meet the 40 micrograms per liter at the lower portion of the lake, Highway 50 and down. Stage 2, where we have the adaptive management provision, requires the reduction of phosphorus of 77% and nitrogen 40% from all developed land in the watershed as of 2006. So that is an extremely difficult, one of the most restrictive and difficult nutrient reduction requirements anywhere in the country. And it also represents something that's not really technologically possible to retrofit. And remember, these local governments do not have the ability. The legislature took away the ability to use condemnation on land in order to install retrofits. They can't do that. So they have to have the owner's permission to install retrofits to reduce nutrients from developed areas in there. And as I said, it limits, it exceeds the limits of technology. There's also uncertainty as to whether the chlorophyll A standard can be met under any circumstance. The modeling that we will do will help us do that. And so the total cost of stage 1 and stage 2 is estimated to be $1.5 billion. That's $1 billion. B, there's about 250,000 people in this watershed. So that's a tremendously high cost for the number of residents in this watershed. As I said, the consensus principles, the one thing about the Falls Lake that I really admire is all of the folks who are at the table. City of Raleigh is the user. They have a small part of their area, their jurisdiction in the watershed, but it's mostly the other folks in the watershed. But they're all at the table. They're all discussing what needs to be done. They're all committing to provide resources to address this problem. And that's a great resource because we have the ability to work together. And so we're continuing to do that. This, long before I became the executive director, they were already working together and talking together about how they could protect this watershed, how they could continue to meet uses in the lake. The lake is meeting its uses, recreationally, fishing, habitat, and also water supply. So the framework for our reexamination, which is the fulfillment of the provision in the rule that allows to look at stage 2. And so we want to develop the information, the data that we need in order to feed into a development of models. We're going to take those models and we're going to do all kinds of scenarios on management, and we're going to come up with a strategy, a improved strategy for stage 2, which we would come with a proposal to the North Carolina Environmental Management Commission, the Division of Water Resources, and also the legislature to find a better and more effective way to manage the nutrients. Here is the slides will be available on the website following the meeting. Here's a list of all kinds of documentation that we developed leading up to doing the sampling from 2014 to 2018 and doing the modeling. So we have a very extensive background in how we came up with our program. This lake is probably the most monitored lake in the Southeast, at least from a watershed and lake combination. There were 38 stations in the watershed. This is a 750 square mile watershed. We had every single tributary monitored that's going into the lake. We looked at storm flows. We looked at baseline flows. We did some flow monitoring, monitoring where we would catch the data, collect the data at higher flow periods to provide that. We have also the benefit of the North Carolina Policy Collaboratory that folks are here today to tell you what they've been doing. But I just want to say that we've had a great working relationship with the collaboratory. They've been doing studies that are going to provide additional support to our effort, provide additional research and insight to how the lake functions that we can build into the models. Just to give a quick rundown of that, on the watershed modeling, we've looked at stormwater retrofits. That's part of the study that the collaboratory has done. On-site wastewater treatment systems, the folks from East Carolina were here today, see them in the back, that were there part of that study, and we've worked with them on modifying the watershed model so it's more reflective of what is being contributed from on-site systems, both those that are subsurface and those that discharge. The collaboratory has been doing water movement studies, nutrient reaction rate studies, lake sediment processes, looking at how nutrients are cycled in the lake, which is extremely important. We've also looked at use designation. Algal toxin evaluation is helpful. And then carbon recycling. Carbon is a big issue with the city of Raleigh. Carbon TOC is a precursor for secondary disinfection byproducts. That's a problem for almost every surface water supply in North Carolina and across the country, because that total organic carbon, when you chlorinate it, becomes other compounds that are known carcinogen. So you've got some issues dealing with that, and we need to evaluate that as well. But funding this and managing this is also important, and the Center for Environmental Financing at UNC is also engaged in that, and community outreach. We'll be doing a symposium on the 7th of April with the Collaboratory and the UNRBA, and we'll be going through that research. You're certainly welcome to come and be a part of that. It's going to be at the Arboretum at UNC, I guess, so in Chapel Hill. So that'll be a good opportunity as well. So we've done a bunch of special studies in the watershed. This watershed, you'd be amazed at how much data that we've got on weather conditions, on the monitoring of rainfall, and the monitoring of movement of weather in that area. The model that we've set up, the WRRI model, the watershed model, is extensive. It looks at how many sub-basin things have we got in there? 264 sub-basin areas that we're calculating runoff from and evaluating that. So we've done a lot of evaluation. I know that the folks from the Collaboratory and the Center for at UNC, Mike's going to be up here talking about the denitrification work that he's been doing. So those are all input to the way nutrients are cycled in this watershed. Nutrients, the balance of nutrients in this lake and in this watershed is critical in terms of looking at the supply of materials that help the algae maintain the algae and grows the algae. Again, we've provided a lot of different studies. One of the things that's extremely interesting in this reservoir is because it is a flood control structure, the Army Corps of Engineers manages the lake for controlling floods downstream. It's hard to see this graph, but this is the variation of residence time in that reservoir looking from 2014 to 2018. As you look at this graph, you can see the wide variation of residence time. Residence time is one of the #1 reasons for the growth of algae. As longer the algae stays in the lake and interacts, the more likelihood you're going to get blooms or you're going to get heavy growth of algae. So those factors are probably more important than the loading to the lake. And that's extremely important as we move forward. There's been a lot of improvement. One of the presentations today talked about deposition of nutrients from the atmosphere. From 2000 to 2019, there've been 26% reduction in deposition from the atmosphere, wet and dry deposition. Total nitrogen loads that are coming from wastewater treatment plants have dropped by 24%. Total phosphorus loads from wastewater treatment plants have dropped by 69%. If you look at the flow-weighted nutrient concentration in the watershed by tributary, you can see over the time from 2005 to 2018, the drops that we've seen in flow-weighted. Now, there's been lots of improvements in the lake in terms of loading. However, you look at the chlorophyll A values in there, and they're still showing significant levels of chlorophyll A over the 40 micrograms per liter. And that is an indicative of how resilient this reservoir is to nutrient management. It keeps the nutrients, the soils keep the nutrients for a long period of time. The lake keeps the nutrients and cycles those nutrients. It is going to be very difficult to see changes in this reservoir except over a long period of time. It's not going to happen overnight. And the status of the reexamination, we're developing and calibrating the models. We're applying the models. Alix will review that in a moment. And we're developing a revised nutrient management strategy that we're going to recommend to the Environmental Management Commission and the state, the Division of Water Resources. So these slides will have this additional information on the website. And as I said, there's my contact information if you'd like to ask me any questions. So with that, are there any questions? Okay, thank you. Steve Wall. That's your introduction.
Good afternoon, everyone. I'm Steve Wall at UNC Chapel Hill. I'm with the UNC Institute for the Environment, and in that role, I also serve as the outreach director for the NC Policy Collaboratory, which I'll talk about just briefly. So in 2016, the state legislature established the Policy Collaboratory at UNC Chapel Hill, and the purpose of the collaboratory is to disseminate the environmental research and expertise of the UNC system for the practical use of state government and local government. So the collaboratory is headquartered at Chapel Hill, but we work across the UNC system and fund projects all across the campus. And you'll see all across the system, and you'll see examples of that as I get into a little more detail about the Lakes project that we're working on and talking about here today. So my role here is not to talk about the science. It's really to talk about context and how this project got started, why it was funded, the commitment by the legislature to this project, and how we've engaged with a lot of partners and external stakeholders over the last few years. So going to give some background on that. Then we're going to briefly talk about the Jordan Lake study that was done in conjunction with the Falls Lake study. And then I'll move on to the Falls Lake information very quickly. So in 2016, the same year the collaboratory was established, the budget bill also contained a provision directing UNC Chapel Hill to do this multi-year study on Jordan and Falls Lake. And at that time, the UNC chancellor decided, well, this is directed to UNC Chapel Hill. The collaboratory has just been established. So we're going to give this major study to the collaboratory. So the collaboratory has been managing the study ever since. And we get $500,000 every year. We were directed by the legislature to start the study by looking first at Jordan Lake, which is what we did, and then transitioning to Falls Lake, which is where we're at now. A couple other key points just to demonstrate the commitment by the legislature and their interest in this topic. In 2018, they provided an extra $1 million for a modeling work to support the Jordan Lake project. So Dan Obenauer here at NC State and Jim Bowen at UNC Charlotte led that modeling work and worked with DEQ pretty closely to put those models together. And that's been a really helpful thing to think about how management decisions can be made in the Jordan Lake watershed. Interestingly enough, we were had a final report due 2023 for this project, but we had no funding coming forward for the last year because of the way the original legislation was set up. But in the last budget bill, the General Assembly allocated another $750,000 for the work. So we've got another round of funding and research that we're going to be doing and are working with UNRBA to develop priorities for that research as we go forward for the last 18 months of this work. So briefly about Jordan. We started our study with Jordan. The legislation that established the study directed us to study certain things, but it also gave us a little bit of flexibility. So the 2 bullet points I have here on this slide are really what the focus of the study was. I want to emphasize at this point that before the study even began, we did a lot of engagement work, both at the department level with DEQ. They've been a great partner through this entire process. We did a lot of work with industry groups throughout the watershed in Greensboro, Burlington, and talking about issues about what should be studied, what are the concerns. The NGOs, Peter Robb is here from American Rivers, and the North Carolina Conservation Network were both really helpful in thinking about how the study should be done and what components needed to be looked at and what expertise the university had. Because we're not working as a consulting firm, we're working with really focused research that can have an impact and that we can identify management actions that are going to make a difference in the watershed. So I did want to point out that engagement work preceded the study. It happened throughout the study. We had annual symposiums with more than 100 people there every year to talk about our researchers were sharing information, but we were also collecting information from the audience as well and external stakeholders about key things that they wanted to see as part of the study. Again, the research team includes a lot of people from UNC Chapel Hill, but it also involves folks at NC State and UNC Charlotte did some really critical modeling. So that's one of the interesting things about this Falls Lake project. It's Falls Lake and the Jordan Lake project. It's a great model for how the collaboratory works. We have faculty from across the UNC system working jointly on very specific projects. We're identifying them as a research team and bringing them together. And then we're sharing those results back with the legislature and state agencies and the state policymakers as well. The Jordan Lake study was finalized in 2019. We submitted our report to the legislature, and part of that process involved a stakeholder kind of engagement group around Jordan Lake that kind of sprung up and the collaboratory helped inform. So I've just got on the screen a couple of the recommendations that have been made. And at this point, I do want to brag on Mike and the rest of the research team, we had to go, once the report was done, we presented a couple of times to the Environmental Management Commission, who was very interested in our Jordan Lake findings and study that we had done. And Stan Myberg, who was the chair of the EMC at the time and former deputy administrator, EPA for many years, when Mike got through presenting, said, "This is the most comprehensive watershed report I've seen in my entire career." And that's high praise from Stan and just a reflection of all the great work that our research team did. So our expectation is that a lot of the work that was done in Jordan Lake will continue to help the Department of Environmental Quality as they go through the rulemaking process and continue to develop a new management strategy for Jordan Lake. So in 2019, we transitioned to Falls Lake. I've got some just quick things that we're doing in Falls Lake. And one of the things is we had the chance to learn in Jordan Lake about some of the research priorities we need to address and some of the things that maybe we didn't need to address, because Falls is definitely different than Jordan Lake, but there was a lot of similarities. We kept a lot of the same members of the research team, but we also transitioned a little bit, and with the help of UNRBA, identified a couple other projects that could really bring value to the work we were doing in Falls Lake. So that research team looks a little bit different. We have, again, some more folks at NC State. Astrid Schnetzer is doing a lot of work around toxic algae in the lake, which we're interested in finding out about. The folks at ECU are part of this project as well, looking at bioreactors in the watershed. There's a great poster here today in the conference room if you want to go check that out when you have a chance. But so it's, again, a really critical research team, and Mike's going to get into more details about that. Forrest mentioned the symposium that we have coming up on April 7th. The symposium, if you care about Falls Lake, want to learn more about Falls Lake and want to hear more about from all the research team, please come out. The symposium is free to the public. It's going to be held at Botanical Gardens in Chapel Hill, and grab me after the session if you want to learn more about that, and we can get you registered for that. So with that, I'm going to turn it over to Mike to talk a little bit more about the research as part of the study.
I have to wait until my time's up. Yeah, one of the things they wanted us to do because of wanted to hold on. You didn't talk long.
Well, I thought this was a lightning talk, but then I saw Forrest was on the agenda. And I knew it wasn't a lightning talk.
It's going to be like a thunder thing comes after you. But here's an opportunity for you to ask any questions while we're waiting a couple of minutes here. We don't want to stay sort of on cycle. That's what they asked us to do. So please ask some questions.
You can ask all the questions of Mike. He's coming up next.
We're good. Yeah, thank you. Thank you. Appreciate it.
Don't leave a preacher with 10 extra minutes.
That's true. That's absolutely true. Well, I'll just say that, you know, Steve said the working relationship between the UNRBA and the collaboratory has been great. And Mike Piehler with the Institute for the Environment has been great too. And we've had a lot of good interchange, and we met with Steve, I guess, a couple of weeks ago to talk about next year or this coming year to have some research that's done then. So I think we have a good combination of what I would call pure research, academic research, along with the work that we're doing through the modeling, which is more directed toward a management strategy and to see what we need to do relative to how to effectively manage this watershed. And uses is very important. The information that Astrid has developed on toxic algae will be greatly helpful in terms of making sure that we're protecting all those uses in the lake. So I think that's going to be extremely helpful. Because use support and use protection is the #1 aspect of the water quality standards and the classifications. North Carolina classifies its water for uses. So we need to make sure we maintain those uses. And that's another good thing about the commitment of the UNRBA is all the members support the idea of protecting the uses for the folks downstream and for the folks in the community. This is a regional resource for the community. I mean, there's a lot of fishing and recreation that goes on. Many of you may have been out there on the lake. So anything else before we move on? We're close anyway. I'm just gonna let Mike. Well, that's okay. Well, you can talk for, hey, Peter.
All right, I'm gonna just project from back here and hopefully the mic will pick it up. I noticed in your presentation you did not touch on the interim alternative implementation approach. Will that come later, or can you
Well,
Time right now and talk about
yeah, that'd be great. I appreciate that. Thanks, Peter. That was a good setup. Thanks, Peter. The IAIA, the Interim Alternative Implementation Approach, which is a alternate way to look at trying to offsetting the impacts from existing development and other activity in the watershed. The rules call for reduction of existing development impacts. Stage one, the wastewater treatment plants achieved much more reductions than they were required to, so therefore we met the requirements for that. But the UNRBA membership said we want to continue to make progress. And as a result, we came up with a proposal to invest money in projects. That includes retrofits, land conservation, a whole list of activities that would provide additional benefits in the watershed. And it's an interim approach because when we get the rules we adopted, we'll have a final approach on how to do with existing development. This is an investment-based system. In other words, every jurisdiction, all of the jurisdictions in the watershed committed money for every year for the next 5 years to install and acquire land and do other projects in there. So, and that was a effort on the part of not only the UNRBA, but the environmental community. Peter was very instrumental in that, and Grady McCauley, and we worked with them on coming up with this IAIA and the details. Of course, the devil's always in the details. It was a great idea. Took us 3 years to get the thing into a package that we could submit. But we're going to be investing, the jurisdiction is going to be investing $1.5 million a year for the next 5 years on projects in the watershed. More money than that's actually going into it. We hope that that will be a model for the future. So thanks, Peter. Mike?
I don't think quite yet.
You're not ready? Yeah, okay.
I am ready, but I think we gotta wait.
I'm gonna have to tap dance you. Well, so you got one, and does anybody else have a Cam, you got a question back there? You said. But you on the spot. Where's Tedder at? Tedder, you got a question? Well, I mean, you know, what I will say is that I've been doing this for 46 years. I went to work for the state in 1976, and I am very proud of this project for the people that work in it. The organizations have been great. This combination between the collaboratory and the UNRBA is unique. This is a unique program in North Carolina. The local governments will have invested over $10 million in studying this lake and evaluating this lake and building models. $10 million. That is unprecedented for a regulated community to put that kind of money into a project to find out what needs to be done to protect the water quality. There's probably no other greater investment on a water body than except what the power companies have spent on their cooling lakes over the years. And this lake is by far the most monitored in the watershed than any other drainage area that I know of in the state. And because of that, we have a unique opportunity to set an example for others. We hope that this kind of integrated activity with the regulated community, a watershed organization, the environmental community, the research community, and the regulatory agency. We have a great working relationship with the regulatory agency. Steve mentioned the regulatory agency working with the collaboratory, but we have every meeting, we have members from Division of Water Resources at our meetings. Our meetings are open. You can go to our website. You're welcome to attend. Right now, we're still doing them virtually, but you're welcome to sit in on those meetings, participate in the meetings. I think Peter will tell you that we're very open to answering questions. We work for complete transparency in what we're doing and the work that we're performing, because we feel like that's the best way to generate support for the direction that we're going in. A lot of times people assume that because you're a regulated community that you're going to be fighting against regulations. And we're not fighting against regulations. We're working with the regulatory agency to get the regulations right. And that's something that we want to do. And Jordan and Falls, by the way, are the first two water bodies in North Carolina to have requirements for existing development. The lower Neuse has the buffer rules and it has the point source control program, but it does not have a program to reduce impact from existing development. And so this is a test. In Jordan, they've not been implemented yet. The new development rules and the existing development rules have not been implemented in Jordan. But in Falls, the new development rules have been in since 2012. So every acre of land that's developed in this watershed must evaluate stormwater impacts. It must get an approval by the local government before the project can be built. And that is unique and unusual in the state. No one else is doing that relative to nutrient impacts. We do it for other stormwater impacts, but not for nutrients. So it is a progressive way to deal with the impacts of nutrients in this watershed and any watershed. So we're breaking a lot of new ground. Alice is going to show the stuff on the information on the watershed model, and that's going to be really earth shattering too. So Mike.
Yeah.
Thank you.
Maybe she's got them open on there.
I was any good. I would have done that.
You did really well.
All right. Thank you, everybody, for sticking around during the rain delay. I will tell you, this has been a delightful experience, beginning in a very different place in Jordan Lake, where we were, I won't say information poor, but we were certainly learning things we needed to understand the sort of fundamental foundation. Whereas when we came to Falls, as you've already heard from Forrest and heard from Steve, these things were in place. And so it was a matter of, what else do we need to know? And the thing that's been so fun is to think as a group. As a scientist, it is a great deal, brings a great deal of pleasure to be able to work with people who are focused on the decision-making, who know what questions they want to answer. And then look then beyond those questions they know they want to answer and think, what else might they need to know? So that's really where we ended up with Falls. It's been a lot of fun. I think we've done really good work. I will tell you the symposia are actually quite fun, so everybody please come. We have delicious food as well, and it'll be in person, which will be a-okay. But what I'm going to talk to you about today is the most recent work from this project. And with it, I'll layer in a little bit about the genesis of the individual projects, whether they were things that were directly identified by UNRBA or that perhaps as individual scientists and individual disciplines we knew were likely to bubble to the top later on. So didn't introduce myself, Mike Piehler, Director of the Institute for the Environment. I'm happy to be working on this project funded by the Collaboratory, which Steve alluded to is a great model. We talk a lot. I'm sure anybody who writes proposals has heard about convergent science. It's a new name for focused team science, trying to find multiple disciplines, working together, having a little bit of a shared language and a shared understanding of issues, and working on problem solving from the jump. This project and Falls also were wonderful in that in the room were the funders and the people who are going to use the data from the beginning. So as scientists, we sometimes can go a little bit far afield and gather information that may be fascinating, but not terrifically useful. And I think in this exercise, we've had a great balance. So that has been very rewarding. So Steve's already showed this slide and offered the history that this project was funded maybe even shortly before the Collaboratory existed or about the exact same time. So it is something that's been going on for several years. We are very fortunate. Steve described that lag between when our final report was due and our funding. So we are extremely grateful to be funded through the final report, which is much more of an optimal situation than it would have been otherwise. So I'm going to provide an overview of the study quickly. I'm going to work through the research team, which is vast and great, and then try and move through the research findings with slides that are a little bit more detailed than I would typically use. I'm a big picture guy. I show pictures and I talk about it. But I thought maybe this level of detail could be more useful in this format because everyone will have access to these slides afterward, and perhaps more of the information we'll carry with you as we finish up today. So it was a great research team. As Steve said, not exactly, and is a great research team, not exactly who we worked with in Jordan. There were needs that we had in Falls that we didn't have in Jordan. And there were certainly needs in Jordan that didn't carry over to Falls. It includes a lot of people from UNC Chapel Hill, from NC State, from ECU. See a lot of folks in the room today. It's great that you're here in case the questions get hard at the end. I will certainly turn to the experts. We did meet early, and while these are individual pieces of a study for certain, there is a level of integration and shared understanding of what everyone's doing that I think has in many cases been really successful in transferring information and results from one project to another so that we weren't working in a silo. In addition, because we were reporting so frequently with UNRBA, I think it was really a good situation for people not going off on their own into the woods and doing things that perhaps wouldn't be as of much value. So here are some of the results. And these are the slides that I was talking about. They're a little busier than I would typically provide. But this is a slide that represents Rick Ludick and Harvey Symes' group. In Falls Lake, I'll start with, where they completed their analysis and their insights have already been gained. In Jordan Lake, forgive me, I'll start with, they found the really interesting phenomena of the Haw River having much more of a role in transporting water to the whole of the reservoir. So that was pretty revolutionary, because that's a big, significant portion of the total source of water, total source of nutrients to lakes that largely was regarded as likely to go over the dam. And the fact that it went up into the lake really changed our understanding of how Jordan likely worked. In Falls, they've been doing similar work. They've got thermistors, they're measuring flow using Doppler velocimeters and also using ADCPs. At this point, their findings have been a lot more conventional. What they've informed, though, is what Forrest pointed out, which is really sophisticated measurements of residence time. And so not just residence time for the lake, in air quotes, but all of the pieces of the lake. And I think Forrest alluded to it a little bit, but there's a lot of heterogeneity within the lake. Within the arms, there can be really widely disparate values for important indicators like chlorophyll. And so if we're going to support a standard that considers the lake as pieces instead of just a whole, certainly this hydrologic understanding is critical. And I think that we're very close to having the information that's going to inform those sorts of analyses. So I think Steve mentioned this work already. The ECU group, many of whom are in the back, great to see you all, did a very focused study looking, we often talk about septic tanks and the challenges of looking and seeing where you have challenges within a system and whether or not you can have targeted approaches to address them. More often than not, it's just septic tanks are problematic and we know we have greater than 50% or whatever our number is. But this study was great in that it identified specific areas within the watershed where interventions might be made and also tested potential interventions that could happen. So this sort of site-specific information is critical. Forrest talked about how difficult the nutrient reductions are going to be to meet, but they'll only be possible with approaches like these. So this has been a wonderful addition to the study. This is work that Nathan Hall and Hans Perl did, looking at the balance between nitrogen fixation and denitrification. So quick nitrogen cycle lesson. Nitrogen fixation brings in new fixed nitrogen from the atmosphere. Denitrification takes fixed nitrogen out of the water and puts it into the atmosphere. Denitrification, I think many of you are well-versed in this process and know that we pay a lot of money to have it happen in sewage treatment plants and stormwater structures. And understanding how it's occurring in the natural system is really important to understanding the balances of all these things that are trying to be managed in the grand scale to reach these goals for the indicators like chlorophyll. So a lot of this work was measurements of nitrogen fixation and then using mass balance models to understand denitrification and comparing those two. And you can imagine that knowing that balance well is really critical to your overall understanding of the nitrogen budget in the lake. So this work was very informative and very, in some ways, surprising. Sometimes I think people are surprised to see nitrogen fixation as many places as they do in areas where the ratios of the nutrients might not predict them. But this is, again, another piece in that puzzle of trying to reach this Herculean goal of the nutrient reductions, but also doing it with full knowledge of how the lake is working. So I'll use speaker's prerogative, even though the work that I did in this area is not from this year. I'll mention our denitrification work that Forrest mentioned. The measured rates of denitrification were a little bit higher than some of the mass balance rates that Nathan calculated. So we've been working together to try and understand why is that, what do we think might be driving those differences, and what do they mean to the management of lake? Because our measured denitrification rates found that that process in lake sediments could contribute to a significant removal of the total load of nitrogen. So we're just working now to find, where is reality between these two slightly different approaches, but very complementary approaches. And I think that that will be of great value to the things that Alix is going to talk about in just a few minutes. So we're also fortunate to have Astrid Schnitzer working in Falls Lake and understanding the distribution of toxins. And really importantly in this work, looking to see if the toxins are well predicted by chlorophyll. So Forrest talked about, what are the right indicators for the function of the lake. We know that 40 micrograms per liter is the chlorophyll standard, and yet we know the uses are still being attained in Falls Lake. One of the great concerns is if you have tons of algae and they are harmful, do you have toxins? And so far, I think Astrid has found there are toxins, but they tend to be below the levels that are of significant concern. But it is probably a difficult thing in terms of future management that the toxin concentrations are not well predicted by the chlorophyll measurements. So again, just another piece of information to, there are some conventional ways to look at the algal community as a whole, but perhaps they're not going to do as good a job as we need in predicting toxin concentrations. So this is work done by Brent McKee, and Forrest mentioned organic carbon being problematic because when it gets disinfected, you can have byproducts and they can be carcinogenic, they can be toxic. Brent's work is also interesting because it's looking at TSS loading to a reservoir that we know has a finite volume and is filling. So what is it? It's only 40 years old, a relatively young person. However, it does have a defined lifespan. And Brent's work has been really interesting because it's looking throughout the watershed and understanding the relationship between TSS loading and discharge. And unlike the slide I just presented, where there was not an easy relationship between the conventional metric and what you wanted to know, there is a good relationship here between discharge and TSS. So if you have a sense of the water going into the reservoir, you have a good sense of the TSS that's coming in as well. In this case, forgive me, total suspended matter, TSM. So this has been a useful thing in terms of just the utility, understanding how long the reservoir is likely to continue being open and being a bowl that will receive water. But also if you think about things like carbon sequestration, if you think about the things that Forrest talked about with the potential for the generation of problematic compounds, it's really nice to know that if you know discharge here, you're likely to be able to predict TSM as well. So this is work that Nathan Hall, who's right there, and I did. And this is looking at the site-specific numeric nutrient criteria and trying to understand, sort of in a fundamental sense, what are we aspiring to be? We know that these reservoirs, Falls, Jordan, all of the southeastern reservoirs pretty much, are not conventional lakes, and they really can't be held to a standard of a conventional lake. So looking at things like the food webs, and particularly the connection between phytoplankton and zooplankton, is informative for a lot of reasons. But the two that we were most interested in is, what are these systems really? And what should we hope they should be if we manage them well? And we were also interested in, are there any opportunities through the food web to assimilate problematic phytoplankton? So we know you've got the grass growing and the cows eating it, and you have too much grass, cows can't eat it. Same thing with the phytoplankton and the zooplankton. Too much algae, zooplankton can't eat it. Unfortunately, well, we did find really similar relationships between other reservoirs, which was interesting, but we didn't see a great capacity for something like biomanipulation or for having a carbon sink in zooplankton. So I would say really informative so far, not necessarily a great opportunity for an unconventional or a less conventional management strategy, but anything new we know about the food webs of these reservoirs, I think is a big benefit. First off, we can quantify what exactly they are. And second off, we can look to see, are there opportunities perhaps to have some of this excess carbon going up into the food web, going to zooplankton, maybe going to sport fish or something great like that. But so far, we haven't seen clear evidence of that in this work. And we're going to continue, Nathan in particular is going to continue this work on into the next year and think more clearly and more specifically about how all of this relates to the 40 micrograms per liter and how that might be thought again in terms of the correct standards for these systems. So Forrest mentioned the work in the Environmental Finance Center. I'm pretty sure everybody's probably pretty familiar with them, but they're in the School of Government at UNC, and they do remarkable stuff. And the whole idea behind our model of problem solving was, okay, how does this reservoir work? what are the problems? What might be the solutions? And then the big one, how are you going to pay for it? And so the Environmental Finance Center has done a lot of work on a range of issues, stormwater for certain, lots of different areas of sort of shared environmental challenges. And they have this really interesting framework, and this is small here, so I'm sure it's, well, it's not as small up there, but this idea of revenue sheds. So if you think about a watershed being the area of land where water rains down and flows into a lake, the revenue shed is the area of land where people live who benefit from that body of water. And so it allows you to think about a fee structure that may be more equitable just than the people on the top of the watershed have to pay, because that's where the best interventions are made. So this was really helpful in the Jordan study. And there were several conversations where big municipalities said, absolutely, they'd be willing to participate in something like this. I was never entirely convinced that they knew exactly what we were talking about, but it's a good sign that there seemed to be some sort of an embrace of a shared responsibility for maintaining these water sources, because everyone knows that many of the big benefits, the drinking water, often are for municipalities or areas that aren't in the areas of the watershed where you'd have to make the big interventions to sustain water quality. So finding some way to distribute that responsibility and also to accurately reflect what the benefits are. Forrest alluded to all of the recreational amenities. Certainly real estate on these reservoirs is really expensive. So these benefits are quantified well in this revenue shed system and are also distributed, or a model is created to distribute the money that may be gathered through fees related to those benefits back to potentially trying to sustain parts of the function of the reservoir. So it's been really interesting, really helpful. They have, the Environmental Finance Center works a lot in North Carolina, but they work a lot globally. So they have a lot of lessons that they can bring from other shared responsibility for systems that provide a lot of ecosystem services and just a lot of value, period, as these reservoirs do. So you think we've worked from how does the lake work physically? What is the biology of the lake? What are some of the important sources and potentially ways to mitigate those sources? Natural processes like denitrification and nitrogen fixation. And then now, how do you pay for it? So we've had this integrated model that has tried to first set the stage of how this thing is working, and second, try and find solutions, and finally try and pay for them. And that's where we are today. And we're happy, really happy to have some time to bring all this together, because that is certainly ongoing. The individual pieces here are remarkable. They're beginning already to meld into a collective whole that hopefully will be beneficial both to UNRBA and to the management agencies in North Carolina, and also to citizens. We have, at our symposium, we have a remarkable number of people who are just interested in how these things work. So that is what I've got for you today. I would be more than happy to answer any questions.
We've got a few minutes for questions, so don't have any on the website, but please ask Mike some quick. And I apologize for not introducing you better.
I didn't introduce myself either. So that's a good question. I know about TSS, and so the question is, what's the difference between TSM and TSS? To be honest, I don't know. I know the difference between SSC and TSS, but TSM I think might be just, it's matter instead of solids. Anybody?
I think that's right.
That's the word, but I'm just not certain functionally. Like SSC is the USGS term for TSS, and it's a little different how you sample it. But to be frank, TSM is not one that I have top of mind. Anybody else for a free prize? Absolutely. Yeah, I think TSS is the oldest one. SSC is more modern, and it's sampling through the water column. But I'll check with Brent unless someone knows and wants to win a prize. We have prizes, right, Forrest?
Sure.
Yeah, we do. UNRBA t-shirts. Exactly.
Other questions?
Yes.
Yeah, going back to this slide we talked about, Tom said, I was just wondering for the researchers in the lab who did this to research on Falls Lake, at especially in the context of silent toxin, has the both taken into consideration the fact that microsystem, for example, they have at least 200 plus congeners, and each of them may have different levels.
That is an Astrid question. So forgive me, the Zoom audience, I
reassess like how we evaluate.
Let me apologize to the folks. We got some folks online. They can't hear the discussion back and forth, so.
You want to repeat it or?
Yeah, that would,
Can you
if you
summarize your
could kind
question?
of capture that again. As Mike said, Astrid probably be the one to answer that question.
Yeah, so to summarize, as far as algotoxin is concerned, at least with microsystem, I'm aware that there are several different congeners under a microsystem, and each of them may have different levels of toxicity. So I'm just wondering if I understand that this is based on total number of microsystem concentration, but I'm just wondering, like, because I know last year, 2021, there was a publication from EPA about how microsystem LA is as potent, if not more so than LR. So I'm just thinking, like, would that change how folks look into toxic levels in the water in the future going forward and such? So that was,
you want to go on record, Nathan?
I've got a response from Astrid to everyone. The preliminary data is based on the total MCY measured using ELISA. So
Turns out Nathan was right.
I think, thank you, Mike.
You bet.
Have another question? Follow up on the most common conogens is planned. That's what Astrid is saying. She's going to do some follow up on those common components of the algal toxins. And Alix Matos is next, and she's going to speak about our modeling effort. And so she's been on this project as long, actually a few months before me. So
That's right. Okay. So yes, I'm Alix Matos. Been working on this project for 10 or 11 years now. And before I get started, we're going to talk about the modeling, the watershed modeling mostly, and then give a little status update on some of the lake models. But I also want to acknowledge our modeling partners at Tss Water Resources and also Dynamic Solutions. So the watershed model that we are using is called WRRI. That's the Watershed Analysis Risk Management Framework. And it takes a lot of the same types of inputs that you're probably familiar with in watershed models. So we have the meteorology, the land use data, soils data. This model actually takes nutrient application data. So you tell the model every month how much nutrients are applied to each different land use. And then it takes into account the topography and the hydrology. Each of the processes that occur in the watershed, either on the land surface, beneath the surface, in the streams, or in the impoundments, is calculated on a 6-hour time step. And all of these processes are simulated. So this isn't a watershed model where you tell the model, this is my runoff concentration. It's actually taking the information from atmospheric deposition and nutrient application and all of the chemical reactions, and it's calculating that for you at each time step. The model outputs stream flow, water quality concentrations, and also tracks the sources of nutrient loads by source. So our model configuration, we've developed the model for a calibration period of 2015 and 16 and a validation period of 2017 and 2018. Again, it's operating on a 6-hour time step. There are 264 modeling catchments. So we have this 750 or so square mile watershed that's been broken up into 264 smaller areas. And we made those separations to correspond with USGS stream flow gauges, UNRBA water quality monitoring stations, county lines if we could, so that we can start to get into jurisdictional loads. And then, of course, we need to consider where streams come together, upstream and downstream of impoundments, et cetera. And each of these catchments is assigned its specific land use data, soils data, how many types of on-site wastewater treatment systems are present, are they functioning or not, what type are they, et cetera. So we have precipitation simulated across this watershed at 78 stations, and we were able to create these input files from help from DOT as well as the State Climate Office. So the State Climate Office takes the NRBA radar precipitation data and can generate point location files and provided us the 6-hour rainfall data. This may seem like overkill, but when we look across this watershed at annual precipitation depths, they can vary by up to 20 inches of rainfall per year across the watershed. And this is important because rainfall is our key driver of nutrient load variation by land use. So it's important for us to have this variability built into the model. Oops. So we were able to look at the number of storms by size class using this information from the 6-hour NRBA data. And this is just for 4 of those 78 stations. So we're going to talk a little bit about the baseline period for Falls Lake. That's the Falls Lake Nutrient Management Strategy regulatory baseline. That's the 2005 to 2007 timeframe. And then we have our study period where we went out and collected the monitoring data and we have set up these models, and that's 2015 to 2018. So you can see left of the dashed line is the baseline period. And really both periods, most of the rainfall events are less than 1 inch. And this is important because our SCMs, our stormwater control measures, are designed to treat 1 inch of rainfall. So we're fortunate that 85% of the events are beneath 1 inch. And then we get into these, the greater rainfall depths occur less frequently. We really didn't have too much high flow of high precipitation events in the baseline period, but we've had quite a bit in the more recent study period. So our land use data, we started with USGS national land cover data. And as Forrest mentioned earlier, 74% of the watershed area is in some unmanaged state, and most of that is in forest. We know that 10% of the watershed is agriculture, and we were very fortunate. Joey Hester is in the room today from the North Carolina, when he was at the North Carolina Department of Agriculture, provided us county level crop specific acreages that we were able to integrate into the national land cover data set for many more crop types than you usually get out of NLCD. It'll tell you it's pasture, it's row crop. It doesn't do a very good job of identifying really the differences. So we were very fortunate to have this information. And they also provided the nitrogen application rates every year from baseline to our recent period by crop type and county. And this again is information that's not usually available. The urban areas in the watershed are about 13% of the watershed, and most of that is what NLCD classifies as developed open space. And if you look at the satellite imagery, most of that developed open space in this watershed are road rights of way. So we wanted to look at, we have to tell the model how much nutrients we're applying to the watershed and what comes from wastewater plants, et cetera. And so we can compare the nitrogen and phosphorus inputs, the gross inputs that we're applying across the whole watershed from the baseline period and the more recent period. And so our nitrogen inputs to the watershed have been reduced from about 14 million pounds per year to about 9 million pounds per year. So that's a 37% reduction in what we're adding to the system since the baseline period. And this is due about 53% less nutrients or nitrogen is applied to agricultural land in the basin. partly because the crop acres and pasture acres have declined since baseline, but also there's been advances in optimizing fertilizer and crop requirements. There's been a 26% reduction in the amount of nitrogen falling on the watershed from the atmosphere. And then we have a 29% reduction from the major wastewater treatment plants that have spent a lot of money upgrading their facilities and optimizing their facilities. For the phosphorus inputs to the watershed, those have declined from 1.6 million to 1.1 million. So that's about a 29% reduction. 41% of that is due to reductions in how much is applied on agricultural areas. And because we had to assume the same phosphorus fertilizer rates for baseline and recent, we can see that that's due mostly to a reduction in crop acres. And then we had a 70% reduction in the amount of total phosphorus discharged from the major wastewater treatment plants in the watershed, and there are 3. We've also, during this period since the falls rules were enacted, some of the local governments have done a lot of work on existing development retrofits. So Forrest mentioned that they are required to reduce loading per the rules by 40% for total nitrogen and 77% for total phosphorus, which is a lot for an area that's already built out. But they did want to go ahead and get a jump on that, even though the rules hadn't officially been required for existing development. So the city of Durham in the Falls Lake Basin, as of December 2015, had implemented almost 350 projects. And that was about 5 times more than they had enacted at the same time in the Jordan watershed. And part of that is because of the regulatory pressures, and part of that is just the collaborative nature of the local governments and organizations in the watershed, and everyone kind of pushing each other to make improvements. But we need to account for these practices in our watershed model in order to calibrate the stream flows and the water quality observations. So we've mentioned a lot of the research that's gone in the watershed thus far, and we've tried to integrate as much as possible as we've developed and calibrated the models. So we have our USGS stream flow measurements that we're able to calibrate our stream flow, and we have ambient water quality data collected by the UNRBA at 38 locations across the watershed, as well as DWR and local governments. The UNRBA also conducted some special studies. So if we did have a high rainfall event, we would either use ISCO samplers or grab flow sampling to understand how nutrient concentrations were changing when stream flows were higher, because most of your routine sampling tends to get low to moderate flows. And then we have the North Carolina Policy Collaboratory research specifically for the watershed. Nathan Hall is studying denitrification in some of these tributaries and lake arms. And then we had a lot of input from the folks from ECU. They presented their research and it was discussed today, but what doesn't get a lot of, I guess, spotlight is they also helped us identify where in the watershed and what effluent concentrations for all the different on-site wastewater treatment systems that we are simulating. So whether that's a conventional system that's functioning or failing, or it's an advanced treatment system, they were able to give us some information and data to input that into the model. And then one of our really critical studies, this was done by the U.S. Forest Service back in 2008 to 2013 in forested watersheds in our basin. They measured the annual nutrient loading rates from forested areas. And since 61% of our watershed is forest, if we're not simulating what comes off of the forest correctly, we're not simulating the watershed correctly. So it was really important for us to have that monitoring study as a basis of comparison. So of the 8.8 million pounds of nitrogen that are being applied to the system, about 1.65 million pounds is actually delivered to Falls Lake. And some of that is denitrification, some of that is crop harvesting where you're just removing, nitrogen from the system. But of what reaches Falls Lake, about half of that comes from the unmanaged areas in the watershed. Remember, 74% of the watershed is unmanaged. 18% comes from the agricultural areas. Remember, they make up about 10% of the area. The urban lands contribute 15%. Remember, they make up 13% of the watershed area. And then we have about 6% of the load coming from wastewater treatment plants, either the major facilities, which are above 1 MGD, the minor facilities, or sanitary sewer overflows. And then we also have about 6% from wet and dry deposition that's mostly directly to Falls Lake. For total phosphorus, we're applying to the system 1.1 million pounds per year, and about 180,000 actually reach Falls Lake. Again, about half of that is coming from the unmanaged areas, 10% from ag, 11% from urban. We only have 3% of this load coming from the wastewater treatment plants. Remember, they had reduced their loads to the system by about 70% since baseline. So they really have done a tremendous job in reducing the nutrient loads. And then about 15% of the phosphorus load comes from stream bank erosion. Total organic carbon, there's about 13.2 million pounds per year that are delivered to Falls Lake, and about 61% of that comes from the unmanaged lands, 22% from agriculture, and 11% from urban. All of the other, we have DOT roads, wastewater treatment plants, the on-site wastewater treatment systems, they each contribute about 1%. So we do want to just take time to compare our annual loads and our annual precipitation so that we can see the importance of precipitation on loading to Falls Lake. So 2017 is there in bold. There was 45 inches of rain about, and that's close to our average. So that's our average year. And if you look at 2018, that was our wettest year. We had 15 more inches. So we got about 60 inches per rain. And in brackets is the ratio between 2017 and 2018. So we had about 30% more rainfall in 2018 than we did in 2017. But if you look to the right at the total nitrogen loads, the total phosphorus loads, and the total organic carbon loads, they at least doubled or a little bit more than doubled when we went from 45 inches of rain to 60 inches of rain. We also have the ability to look at that 6-hour rainfall data that's in the model and our loads that are passing some of our smaller subwatersheds. So this is just for total nitrogen. Ellerby Creek's on the top, Napa Reeds Creek is on the bottom. They both actually include one of the major wastewater treatment plants. But you can see on days where we have less than 1/4 inch of rain, you can barely make out the daily load that passes that site. And most, like I said earlier, most of the days have less than 1 inch of rain. And so you can see a little bit more. Once we get to 1/4 inch to 1 inch of rain, you can at least start to see blue. But the higher the rainfall depth goes, and when we get up to storms that are 4, 6, 8 inches of rain, we can get hundreds of times more load passing that site than when we had, 0 to 1 inch of rain. And that's including the loading from the major wastewater treatment system. So that was interesting for us to see. So for the lake models, we have 3 lake models that are under development right now. One is called Warmth Lake. It's actually embedded in the Warmth Watershed Model. We're just working on calibrating that now. It has 6 main segments for Falls Lake, and they're each divided into 40 layers. So it kind of looks like you've run layer cakes down the table, the way that they're connected. And then we have the EFDC, hydrodynamic, water quality, and sediment diagenesis model. That also is using output from the watershed model. There are 862 horizontal grid cells that have up to 10 vertical layers. We are calibrating our lake models to compare to the photic zone composite water quality data that DWR collects in Falls Lake. So where and when we need to do layer averaging, we're doing that. We're not just picking the layer that happens to correspond to the bottom or the midpoint of that photic zone. And then the third model is the statistical Bayesian model of Falls Lake. And that's That's using data mostly from 1990 to 2020. Our local data sets are stream flows, water quality, as well as some national data sets. So we want to be able to link water nutrient loading to water quality in Falls Lake to designated use attainment. So one of the data sets that we acquired recently was from the Center of Disease Control. They have a data set called OHABs where states can report hazardous algal bloom events. And so every state is tracking and reporting different information, but at least we're able to see what was your toxin level, what were the human health events, what were the animal health events. And so we can use that information in our model because we don't have very high toxin levels in our lake, but we can use the national data sets to kind of broaden our lens and learn from that as well. So our reexamination timeline, we've basically broken this project. It's been going on for about 11 years now. Our planning, our monitoring, and most of our model setup is done. We've calibrated the watershed model. It's gone through subject matter expert review as well as third-party review. And so we made some final tweaks and got that finalized in January, and we're just working on the model report now. And so we're in the process of calibrating the lake models, hopefully within the next several months. That will be done, and we have initiated the subject matter review process for those as well. And once the lake models are calibrated, then we can use them to evaluate different management scenarios, look at cost benefit information, and start to really integrate our information from our stakeholder meetings. What do people want to see, and how are we going to come up with this revised nutrient management strategy for Falls Lake that is feasible and that people are willing to participate in? And that's the end of my talk. If there are questions, or Forrest, if you want to add anything on this last slide.
Okay. Questions for Alix? Questions? Well, we've covered what we wanted to do today. I think it's fair to say that Falls Lake and the watershed has received about as much attention as it can get from research and evaluation. Alix has done a great job, and Mike and Steve, the collaboratory and the Institute, have done a great job. Our researchers have done a great job. You know, we're going to have to make the leap from what we know to what we do. And that's not always a straight line. The modeling's great, but it won't tell us the answer. It will probably be a long-term commitment to a management strategy that will go on for decades. And we'll probably have to put a reexamination component in it. You can't say, well, you know, we're done. That lake is going to change. It's 40 years old and it's changing. Everyone in here is 40 years old. You're changing. Just know that. I'm changing by more than that now. So, as lakes, like people, are changing. We have different responses. So it is a dynamic system, and we are grateful that we have such a dynamic study process that allows us to do this kind of detailed evaluation, because it's not always possible. I started out writing waste load allocations for effluent limits for treatment plants. I usually spent about an hour calculating what the limits were, and then they would have to spend $10 million to build a wastewater plant. So we're hopefully going to invest more in terms of doing that. But we do thank you for your attendance today. And if you have any questions, we do put our contact information on the slides, and they'll be posted on the website. So thank you.